In this particular section, we're going to talk about working with something called rational expressions. A rational expression was a fractional expression where both the numerator and denominator are polynomials. Now, there doesn't necessarily need to be a variable in the numerator and denominator as long as the expression in both the numerator and denominator are considered polynomials. So 2x over x minus 1 is a rational expression. X over x squared plus 1. X cubed minus x over x squared minus 5x plus 6. Some examples that are not rational expressions or not, I'll do the not polynomial. So if you saw something that looked like this in a numerator or denominator, it would not constitute a rational expression. So if you had something like the square root of x plus 1, not a polynomial. Therefore, if it occurs in a fraction, it's not a rational expression. X to the negative fourth plus x. If you have x to the negative fourth, it's not going to be a polynomial. Yeah, I think those are the ones we normally look for, are square roots and negative exponents. We also don't want to see things with multiple variables in it, but we won't see that. We're only going to see problems that have a single variable. In Algebra 2, we talked a lot about domain and range of a polynomial. Domains were the set of real numbers that a variable is permitted to have. In other words, if there's a value that makes the expression undefined, that value cannot be in the domain. So some examples are 1 over x has a domain of x cannot be 0. Because as you know, 0 is the one number you can never have in the denominator of a fraction. If the expression is the square root of x, then the domain is x has to be every number greater than or equal to 0. Because you can't take a square root of a negative and get a real number. Those were called imaginary numbers, and we're only dealing in real numbers. So 1 over the square root of x would have a domain of x's greater than 0, not greater than or equal to. It's greater than because the square roots have to be positive. And the other reason that it's just greater than 0 is because you can't have 0 in the denominator of that fraction. So here in example 1, we're going to find the domain of each of these expressions. Example A is a general run-of-the-mill quadratic equations. And one of the things we learned in Algebra 2 was that the domain of all quadratic expressions was all real numbers. So one way of writing all real numbers in interval notation was like this. Another way of writing all real numbers you may or may not have run into depending on what teacher you had. It's this weird looking R symbol. It's like an R with an extra leg. And it means all real numbers. Or sometimes you can just write all real numbers, because there's no number in the world that if you plug it into that expression will give you an error message when it comes out. In part B, though, remember anytime you have a fraction, you cannot have 0 in the denominator of a fraction. So anything that makes that denominator equal to 0 is not in the domain. Well, one way of figuring out the answer to this is to factor x squared minus 5x plus 6. That's really the most direct route. There are other ways of doing it. When you factor it, the two numbers that multiply to give you 6 but add to give you negative 5 are negative 2 and negative 3. And then using the zero product property, you find out that if x is 2, the denominator becomes 0 because 2 minus 2 is 0. Or if x is 3, the denominator is 0 because 3 minus 3 is 0. So we say this is the domain. X cannot equal 2 or 3. In part C, the reason I didn't worry about the numerator in part B is because the numerator is just x. But in part C, the numerator is the square root of x, which we already know has a domain of x is greater than or equal to 0. And since the denominator can't be 0, in the denominator x cannot be 5. Otherwise, you have 0 in the denominator fraction. So we say that the domain is x is greater than or equal to 0, and x cannot equal 5. I'm going to add a part D to this because there is another way of looking at the domain, and it's by looking at the problem on your graphing calculator. Now, let's say I want to know what the domain of the square root of x squared plus 3x plus 2 is. First of all, we know that this expression has to be greater than or equal to 0 because it's under a radical, and we know the square root of x has to be greater than or equal to 0. You can't have a negative number under the expression. So one way of doing this is to go to your y equals, and under y1 equals, type in the square root of, and depending on which version of the TI-83 or 4 that you have, the calculator I'm currently using gives me a little square root symbol and then opens a parentheses. So then I type in x squared plus 3x plus 2. If you have a newer version of the graphing calculator, it'll just do this for you. And then, when you're done, go to Second Math. It's called the test function. And when you go there, you'll notice all these inequality symbols. Pick greater than or equal to. Hit enter, it'll pop up on the screen, and then type in 0. When you go to graph, you'll see this very interesting graph pop up on your screen. It basically looks like this. Well, if you remember graphing on a number line, something called a compound inequality, if you look at the little tick marks, you'll notice that this is at 1 and this appears to be around 2. So we would say that x has to be less than, I shouldn't say 1 and 2, those are negatives, sorry. This first part of the graph would be the inequality x is less than or equal to negative 2. And the second part of the graph would be the inequality x is greater than or equal to negative 1. And when you have these two graphs on a number line that point away from each other, we put the word or between them. So this one was a little bit trickier without having used the graphing calculator. There is another way to do it using a number line. It is a lot more involved. This is a more direct way of finding the domain. When we want to simplify rational expressions, one of the first things I always look for is if there's something that can cancel. Now I want you to look at the expression x squared minus 1 over x squared plus x minus 2. One of the most common mistakes that students make is they go, oh, I remember canceling. I see an x squared on top, I see an x squared on the bottom, and boom, they go away, and I'm left with negative 1 over x minus 2. Which is not the right answer. The way that we go about canceling is we have to start by factoring. This is my a squared minus b squared, which factors into a plus b, a minus b. The denominator is a general quadratic where I look for the two numbers that multiply to give me negative 2, but add to give me 1. Well, those answers are positive 2 and negative 1. Now that it's on factored form, I can cancel common factors. That's the only way you can simplify rational expressions. Everything must be factored, and you can cancel common factors. Since I have an x minus 1 in both the numerator and denominator, they go away, and I'm actually left with x plus 1 over x plus 2. And that would be the simplified fraction. When multiplying rational expressions together, now multiplying fractions, you would just multiply straight across, but that's a lot of multiplying. So there must be a simpler way of doing this. Well, the simplified way of doing this problem is to actually factor each polynomial that can be factored, and then start canceling stuff out. So I'm going to start with this expression. It factors into x plus 3, x minus 1. The denominator factors into x plus 4x plus 4, or x plus 4 squared, but I like to write it all out. This is not a quadratic, but it does have a greatest common factor. You can take out a 3, and you're left with x plus 4. This is not factorable. It's not only linear, but it has no greatest common factor. So now I can multiply this together if I want, or since it's just multiplication anyway, I can start looking for common factors. Once I find those common factors to get rid of, I'm left with 3x plus 3 in the numerator, and I'm left with x plus 4 in the denominator, and that's the final answer. You may recall that dividing rational expressions was really multiplying rational expressions. When you're dividing two fractions, it's the same as multiplying by the reciprocal of the second fraction. So basically, I just turned this into a multiplication problem by finding the reciprocal of the second fraction. I just flipped it over. Now, this is just like the previous example. In order to do it, I'm going to do any factoring I can. This is not factorable. X squared minus 4, that's x plus 2x minus 2. X squared plus 5x plus 6 factors into x plus 2x plus 3. And x squared minus 3x minus 4 factors into x minus 4, x plus 1. Now I can find common factors. The x minus 4's go away, the x plus 2's go away, and that looks like it's it. So I'm left with x plus 3 in the numerator, and I'm left with x minus 2, x plus 1 in the denominator. And that's as simplified as I'm going to get. For adding and subtracting rational expressions, we needed a common denominator in order to do it. You can't just add the numerators and add the denominators. It doesn't work that way. Now, if you think about a very simplified case, this is the case I always like to use, 1 over 2 plus 1 over 3. The least common denominator is 6. It's often the product of the denominators. Not always, but often it is. And in this case, here it is. One of the denominators is x minus 1, one of the denominators is x plus 2, so the least common denominator is just x minus 1, x plus 2. That means that I need an x plus 2 in the first fraction, and the second fraction needs an x minus 1. Now I can add these fractions together. The best way to go about doing it is to first distribute the numerators. I'm not going to distribute the denominators. I'm actually going to leave it in factored form. Then once you've distributed, now you're going to combine like terms, and the numerator is going to become x squared plus 2x minus 6. And then you have to ask yourself at the end of the problem, can you factor the numerator? Are there two numbers that multiply to give you negative 6 but add to give you 2? And the answer is no. So this must be the answer. Subtracting, though, you need to be a little bit careful. Let's see, so we're going to do 1 over x squared minus 1 minus 2 over x plus 1 squared. The first thing that I'm going to do is I'm going to write the first fraction in factored form. And then I'm going to change this to plus a negative 2 over this. Now I got to find the greatest common, or the least common denominator. The way that I like to attack the problem is I like to look and say, okay, well, one of the fractions has 2 x plus 1's, and the other one only has 1. So if this one had just an extra x plus 1, And if the second fraction had an x minus 1, then they would both have the same denominator. Or the other way is you can just determine that the least common denominator is x plus 1 squared x minus 1. Now I'm going to distribute the numerator, so I get x plus 1 plus negative 2x plus 2. I'm not going to multiply out the denominators, I'm going to leave them. And then I'm going to combine like terms, so I get negative x plus 3 all over x plus 1 squared x minus 1. And there's really nothing else to do with this. My textbook actually writes this as 3 minus x in the numerator. It really doesn't matter. I'm fine with negative x plus 3.